recommend watching our previous videos about them before moving on in this video. Okay, let's start with just the first two laws on our list, which should look familiar if you watched our video called Exponents in Algebra. They're just the two rules we learned in that video. You know, rules, laws, same difference. So you probably already know them. They simply tell us that anything raised to the first power is itself, and anything raised to the 0th power is just 1. And because we already know about exponents that are higher integer values, like x to the second and x to the third, that means we've pretty much got things covered, right? Ah, not so fast. Don't forget that integers can have negative values too. For example, what if we had the expression x to the power of -1, or -2, or -3? We know that exponents are a way of doing repeated multiplication. But how in the world could you multiply something together a negative number of times? Well, you can't. Fortunately, the next law on our list tells us how to interpret a negative exponent. That law says x to the -nth power equals 1 divided by x to the nth power. And if you think about it, that kind of makes sense. A negative number is the inverse of its positive counterpart. And division is the inverse operation of multiplication, right? So a negative exponent is basically repeated division. X to the -1 would be 1 divided by x. X to the -2 would be 1 divided by x divided by x. X to the -3 would be 1 divided by x divided by x divided by x, and so on. Seeing it like this makes the pattern clear, but mathematicians prefer to express negative exponents in fraction form, where 1 is divided by the same number of x's multiplied together. But since those multiplied x's are all on the bottom of the fraction, you're actually dividing by all of them. Here's an example that will help you see that that's true. 2 to the -3rd power. Let's first try that as a repeated division problem like our pattern shows us. We always start with a 1, so we would have 1 divided by 2 divided by 2 divided by 2. If we do those operations from left to right using a calculator, we get 0.125 as the answer. Now let's write it in fraction form like our law of exponents tells us we can. 2 to the -3rd power would be the same as 1 divided by 2 to the 3rd power. And that's the same as 1 over 2 times 2 times 2, which simplifies to 1 over 8, and 1 over 8 simplifies to 0.125. See, whether you write it as a pattern of repeated division, or in fraction form, like our inverse law shows, you get the same answer. And now you know how to handle any expression with a negative exponent. It's just 1 over the same expression with a positive exponent. X to the -1 is 1 over x to the +1, or just 1 over x. X to the -2 is 1 over x to the +2. X to the -3 is 1 over x to the +3, and so on. All right, 3 laws down, 5 more to go. And these next 5 show us how we can do various math operations involving exponents. In fact, the next law tells us how we can take a number raised to a power and then raise that to a power. As you can see, it shows an expression, x to the power of m, grouped inside parentheses, and then that whole group is being raised to the nth power. It's a nesting situation, kind of like those Russian nesting dolls. So what if someone asks you to simplify the expression x squared cubed, which means the entire x squared term is raised to the 3rd power? Well, our law tells us that we can simplify that by multiplying the exponents together. See how it equals x to the power of mn, which means m times n? That means x squared raised to the 3rd power would be the same as x to the power of 2 times 3, which is 6. Want to see why that's true? Well, think about what it would mean to raise x squared to the 3rd power. It would mean multiplying 3 x squared terms together, like this. And each one of those x squared terms simplifies to x times x, right? So we end up with 6 x's being multiplied together, which is just x to the 6th power. See, our law works great. If you have a number raised to a power, and that's all raised to another power, you can just multiply the 2 exponents together to simplify it. And it works for negative exponents too. Like what if we had x squared raised to the -3rd power? Well, our law tells us that that's the same as x to the power of 2 times -3, which is x to the -6th. To see if that's true, we'll need to use the law we just learned about negative exponents and rewrite this as 1 over x squared to the +3rd power. That simplifies to 1 over x squared times x squared times x squared, which in turn simplifies to 1 over 6 x's being multiplied together. And that all checks out, because 1 over x to the 6th would be the same as x to the -6th power. Pretty cool, huh? Okay, we're halfway through our list of laws, and we're going to look at the next two as a set, because they tell us how we can multiply and divide expressions that have the same base. And that's important because we couldn't simplify them to have a single exponent if the bases were different. The first law says that if we have the base x with exponent m being multiplied by the same base x with exponent n, we can combine them simply by adding the exponents together. And the second law says if we have the base x with exponent m being divided by the same base x with exponent n, we can combine them simply by subtracting the exponents. Let's see some examples of each, like this one, 2 to the third times 2 to the fourth. Does that fit the pattern of our first law? Yep, the base of both expressions is the same, but they happen to have different exponents. The law would still work if the exponents were the same, but they don't have to be. Just the bases have to be the same. Our law tells us that this would equal 2 to the power of 3 plus 4, or 2 to the 7th power. But does it? Well, let's break it down and see. 2 to the third is 2 times 2 times 2, and that's being multiplied by 2 to the fourth, which is 2 times 2 times 2 times 2. That's a lot of 2's being multiplied together, 7 2's to be exact. Aha! So that is what you'd get by just adding the exponents together, since 3 plus 4 equals 7. And this law makes total sense if you think about what an exponent really means. The exponent is telling you to do repeated multiplication of the base, right? So this first part is telling you to multiply 3 2's together, and the second part is telling you to multiply 4 2's together. So that's why you can add the exponents together if the base is the same. Or think about it like this. If we had 10 x's all being multiplied together, we could form different groups of them and combine them using exponents. Like we could combine the first 4 x's into x to the fourth, and combine the remaining 6 x's into x to the sixth. And of course those expressions would be multiplied together since all of the x's were being multiplied. But you'd probably never want to do that, would you? I mean, why not just combine all 10 x's into the expression x to the 10th? But there you see that our law holds true. X to the fourth times x to the sixth would equal x to the power of 4 plus 6, or x to the 10th. Okay, now let's move on and see some examples of the second law in this set, which tells us how to divide expressions with the same base. Suppose we have the expression 5 to the third power divided by 5 to the second power. Our law says that we can simplify this by subtracting the exponents. Specifically, we take the exponent on the top and subtract the exponent on the bottom from it. If we do that, the simplified version would be 5 to the power of 3 minus 2, or 5 to the first power. But is that right? To see, let's write the expression out in expanded form. On the top of our division problem, we have 5 to the third, which is 5 times 5 times 5. And on the bottom, we have 5 to the second, which is 5 times 5. Does this look like something you've seen while simplifying fractions? Yep, since all the bases are the same, they form pairs of common factors on the top and bottom that can be canceled out. This 5 over 5 cancels, and this 5 over 5 cancels. If you don't know why that works, be sure to watch our video about simplifying fractions. And what do we end up with? Well, all the factors on the bottom canceled out, which leaves 1 since there's always a factor of 1. And there's only one 5 left on the top. So our expression simplified to 5 over 1, or just 5. Following our law, we got a simplified version of 5 to the first power, which is also just 5. So it really did work. But to make sure you've really got it, let's try using this law again with the expression x to the fourth power over x to the sixth power. This one's interesting. Our law says that we can simplify it by subtracting the bottom exponent from the top, right? But in this case, that will give us a negative exponent because the bottom exponent is bigger than the top. 4 minus 6 would be negative 2. So according to our law, this expression should be equal to x to the negative 2. Let's try writing it out in expanded form to see if that's true. On the top, x to the fourth would be the same as 4 x's multiplied together. And on the bottom, x to the sixth would be the same as 6 x's multiplied together. Once again, we see that there are pairs of common factors that we can cancel. 4 pairs to be precise. And when we cancel them all, we're left with a 1 on the top, because there's always a factor of 1, and only 2 x's multiplied together on the bottom. If we recombine these 2 x's, we get 1 over x squared. And if you remember the law we learned earlier about negative exponents, you'll see that 1 over x squared is exactly the same as x to the power of negative 2. So these laws really do work. Okay, it's finally time to look at the last 2 laws on our list. And fortunately, they're pretty easy ones, so we're not going to spend too much time on them. These laws look kind of similar to the last pair. Just like before, the first one involves multiplication and the second one involves division. But notice that in these laws, the bases are different, but the exponents are the same. That's the exact opposite of the situation with the last pair of laws. It turns out that these laws aren't about simplifying exponents, they're about how you can distribute or undistribute a common exponent to different bases. The first law shows this group, x times y, that's being raised to the power of m, and it says that you can rewrite it as x to the m times y to the m. In other words, you can distribute the exponent to each factor in the group. And the second law shows the group, x divided by y, that's being raised to the power of n, and it says that you can rewrite it as x to the n divided by y to the n. In other words, you can distribute the exponent to each part of the fraction. Of course, these laws would work in reverse too, and you could undistribute the exponents if they're the same. For example, if you're given the expression x squared times y squared, you could rewrite that as the quantity x times y squared. And if you have the expression x squared divided by y squared, you could rewrite that as the quantity x over y squared. Here are two expressions that will help you see why you can distribute or undistribute exponents like our laws show. In the first expression, we have the quantity x times y squared, and that's the same as x times y times x times y. And the commutative property says that we can rearrange those factors like this, x times y. But look, we can simplify that into x squared